I was browsing Reddit and then I came across this interesting question. The reasoning is excellent. If, if the event horizons behaved like a spherical shells, like a ball. But you know what? General relativity tells us something else. True event horizons cannot overlap like two circles in a Venn diagram and then later pull apart again. If the black holes later separate without merging, then viewed using the true event horizons, the horizons never actually overlapped in the first place. Why? Think of an event horizon as a boundary of no return for light. If light starts from some point and can eventually get infinitely far away, that point is outside the event horizon. If light from that point can never escape, that point is inside. The weird part is this: to know whether the light will ever escape, you have to know what happens later. For example, imagine two black holes pass close to each other. At one moment, the gravity around them might look so extreme that you think that region must be inside a black hole. But suppose the two black holes later fly apart and a photon from that region eventually escapes, then looking at the full history, the photon was never actually inside the true event horizon. So, an event horizon is not determined only by what does gravity look like right now. It is determined by, can light from here ever escape, considering everything that happens in the future. And this is what physicists mean when they say the event horizon is global. A useful analogy is a road with a point of no return. You cannot always tell where the true point of no return is from a single photograph of the road. You need to know where the road ultimately leads to. This is why the two black hole idea is subtle. If they later separate and a particle gets away, then the particle was never inside the true event horizon, even if at that moment it looked like it should be. So let's imagine the proposed solution. If we treat those circles as independent Schwarzschild horizons, there appears to be an overlapping region. But in an actual black hole spacetime, you cannot just take radius of black hole A and black hole B, draw their spheres around an object, and call those event horizons. Those formulas describe isolated Schwarzschild non-spinning black holes. Once the gravitational fields strongly interact, the entire space-time geometry has to be solved together, not separately. Now, suppose they are really going to merge. Initially, they can be two disconnected pieces of an event horizon, and as they approach, they distort. Eventually, the event horizons become connected, and from that point onward, there is essentially one common black hole region. Numerical relativity calculations show exactly this transition. Two initially disconnected event horizon components join and subsequently relax toward the event horizon of the final black hole. The space-time diagram is famously called as pair of pants. More accurately, when time runs upwards, two legs become one waist. Now, here's the crucial part. The null rays that generate an event horizon can join the horizon, but they don't subsequently peel away from it toward the future under the standard assumption of classical gravity. Event horizon generators have no future endpoints of the sort that would be required for the horizon to split apart again. So, you can have two horizons merging into one horizon, but ordinarily not one horizon splitting into two horizons. In a classically predictable black hole spacetime, this is closely related to non-bifurcation property of event horizon. Therefore, the sequence that was imagined cannot describe true event horizons. Now let's go to the next scenario. What if the black holes fly past another? Now suppose they approach extremely closely but have enough velocity / angular momentum that they scatter and afterwards they become widely separated, then there was never a common event horizon. Even if some local calculations made it look like as if individual Schwarzschild radii should overlap, the actual global event horizons would distort in such a way that the black hole regions remain separate. That's the strange consequence of global definition. Now consider the particle in question. The proposed particle is here, somewhere between black hole A and black hole B, or exactly in between black hole A and black hole B. Then the question is, could it temporarily be inside both event horizons and then escape one when the black holes move apart? For event horizons, no. Suppose particles cross a true event horizon at point P. By definition, P belongs to this, meaning no future directed causal path from which P can reach future null infinity. Now let's go into this notation. P does not belong to J minus in brackets scribe plus. It looks intimidating, but it expresses very simple idea. From event P, nothing, not even light, can ever escape to infinitely far away in the future. Now let's decode every symbol. P is not just a location space, it is a location in space-time, means P would have coordinate of xyz in the space and time t. So we can imagine P going into the future coming from the past. Now scribe plus, this strange looking symbol actually denotes future null infinity. Conceptually, it means where outgoing light rays end up if we manage to escape forever. Imagine shining a laser light away from a black hole. If that photon keeps traveling outward indefinitely and never falls back, we eventually say that it has reached scribe plus. Now don't think of scribe plus as a physical wall or something few billion light years away. It is arbitrarily far away, arbitrarily far into the future along the path of light. What does this J minus mean? Now this is the important part. J minus in bracket X would mean causal past of X. Causal means connected by something that travels at the speed of light or slower than the speed of light. Now J minus scribe plus means all events which is possible to eventually send a signal into the future null infinity. Suppose you are at event A. You can fire a photon outward and that photon escapes forever. So A belongs to J minus scribe plus. In plain English, it would mean A belongs to collection of events capable of communicating to infinity. Now let's add a slash. P does not belong to J minus scribe plus. It means that there is no future directed path from P traveling at or below the speed of light that reaches future null infinity. And this is exactly what it means to be inside a black hole. There is no contradiction because the location of the event horizon would have been different from what was initially assumed. But there is something very close to this idea. It's called the apparent horizon. And here things get much more interesting. An apparent horizon is a quasi-local time-slice dependent object. Unlike an event horizon, it does not require knowing the entire future space-time. Apparent horizons and event horizons can differ substantially in dynamical situations. During a black hole merger, they can actually be two individual apparent horizons, a common apparent horizon between them, additional inner trapped surfaces. Numerical simulations have found that there are two original apparent horizons that can continue to exist for a while after a common horizon has formed and can interpenetrate before eventually disappearing through a more complicated merging trapped surface behavior. So in a picture like this, where a point lies within several different trapped surfaces, is perfectly possible. But those aren't two independent escape-proof event horizons overlapping. There's another misconception worth fixing. It was said, not enough that the singularities at the center fall into each other's event horizons. We need to be careful with that picture too. A singularity isn't really a little massive object sitting at the middle. And that's the Newtonian style mental picture. For a Schwarzschild black hole, once you are inside, the singularity is more like a future boundary of space-time than a location sitting inside ahead of you in ordinary space. So during the merger, saying one singularity enters the other one's horizon isn't really the best invariant description. The meaningful statement is that the causal structures of two black holes' interiors join into a single black hole region. And the most, well, mind-bending, mind-blowing part, imagine somehow we watch two black holes approach today, but they won't actually merge until tomorrow. The event horizon we assign to them today is already shaped partly by what happens tomorrow, because whether a point belongs to the event horizon depends on whether light from that point can ever escape in the future. So the universe doesn't first say, these event horizons overlap now, let's see later whether the black holes separate. Instead, the complete spacetime has one causal structure. When we look at a particular time slice, we are merely taking a cross-section of that four-dimensional structure. That is why the apparent paradox disappears. In simple English, if a particle genuinely crossed event horizon, no later motion of the black holes can free it. If the black holes later fly apart and the particle escapes, then what crossed wasn't a true event horizon. Perhaps it was an apparent / trapping horizon or surface, or simply a boundary estimated incorrectly by treating each black hole as isolated. The event horizon is fundamentally not an object at a certain distance. It is a structure in a four-dimensional space-time. Looking only at a 3D snapshot is exactly what creates your apparent overlap paradox. Thanks for watching.